Welcome to Part 5 of this week's online lecture. In Part 5 we will continue our discussion of the anharmonic oscillator model. Let's have a look at the effects of anharmonicity. Because the energy levels are getting closer and closer together, the specific selection rule that delta V is equal to plus or minus 1 breaks down. It means that we can see a transition, say, from V equals 0 to V equals 2, or V equals 0 to V equals 3. These overtones become allowed. But the thing is, though, the transitions where delta V is greater than 1 are very much weaker. The way to think about this is that anharmonicity is a small perturbation to the harmonic problem. The harmonic problem rigorously has the selection rule that delta V is equal to plus or minus 1. That selection rule gets broken because of this small perturbation, but because it is a small perturbation, it means that the intensities of anything that breaks the harmonic rule are much weaker. Hopefully, intuitively you can understand that. This happens a lot where you have selection rules. We refer to transitions that break these selection rules as forbidden transitions. But if they are forbidden, why do they occur? Well, that's because the assumptions about those transitions don't really hold in the real world. Harmonic oscillator doesn't really hold in the real world. All molecules are anharmonic. We call them forbidden because they break that ideal model. But whenever you have a forbidden transition, I'm sure you will have noted that the intensities associated with forbidden transitions are very much weaker. There has also been a shift in the energy levels. The energy levels are getting closer and closer together as we approach the dissociative limit. For an anharmonic oscillator, delta V is arbitrary. We can have values greater than 1, but the intensities of transitions where delta V is larger than 1 are very much smaller. We can solve our transition moment and determine what the intensities are. They are non-zero, but they are very much smaller. So we will get more transitions than a single peak. We are going to get a transition from V equals 0 to V equals 2. It is going to be at the frequency of approximately twice the fundamental frequency. The transitions where delta V is greater than 1 are known as overtone bands. If we go from V equals 0 to V equals 1, we get what we call our fundamental band. If we go from V equals 0 to V equals 2, we have our first overtone. And if we go from V equals 0 to V equals 3, we have our second overtone. And they get steadily weaker and weaker in terms of intensity. So you can see why the first overtone will appear in our spectrum at approximately twice the frequency of the fundamental band. But not exactly twice the frequency, because in fact the levels are getting closer and closer together. It will be slightly less than twice the frequency of the fundamental. So if we know what the fundamental frequency is, and we know what the first overtone frequency is, we can get information about the anharmonicity. You can imagine, because we know the energies from the Schrödinger equation of the Morse potential, we can use the information about the frequencies of the fundamental and the first overtone to determine what the anharmonicity constant is for that molecule. The reason why those intensities are getting smaller for the overtones is because the transition moments are getting smaller. I want to now look at the hot bands, which also have much smaller intensities, but for a different reason. Here is our familiar fundamental band. However, we could have a transition from V equals 1 to V equals 2, and this would be our first hot band. We could also have a transition from V equals 2 to V equals 3, and this would be our second hot band. The intensities of the hot bands are very much weaker than the intensity of the fundamental band, but the reason for this is that the population of the V equals 1 and V equals 2 states, which are the initial states for the first and second hot bands, are very much smaller than the population for the V equals 0 state, which is the initial state for the fundamental band. And for something like HCl, or carbon monoxide at room temperature, the intensities are absolutely minute, so you generally don't see them. You'd have to be at much higher temperatures to see the hot bands, or you'd have to have a molecule where the frequency is much smaller, like in a heavier diatomic. If you have a much heavier diatomic, such that, say, the fundamental frequency is just a couple of hundred wave numbers, then yes, you could see the hot bands. However, there will be a difference in the response of the spectrum of the hot bands compared to the overtones as we change the temperature. As we increase temperature, the populations of the excited vibrational states will increase at the detriment of the population of V equals 0 state. This means that the intensities of the hot bands will increase and the intensity of the fundamental band will decrease as we increase the temperature. This behavior is not the same with the overtones. With overtones, the initial state is always V equals 0. So the intensities of the overtones will also decrease with increasing temperature, in the same way that the intensity of the fundamental band decreases with increasing temperature. So what will all this look like? If we were to look at a fairly large spectral region, this is the kind of idealized spectrum we'd see for a diatomic molecule. We can have a hot band, say, of V equals 1 to V equals 2 with a small intensity here. Notice it is at a frequency smaller than our fundamental band. The gap between V equals 1 and V equals 2 is smaller than the gap between V equals 0 and V equals 1, and so therefore the hot band occurs at a frequency smaller than that of the fundamental band. The fundamental band occurs at a frequency of approximately ν-e. The first overtone will occur at a frequency that is approximately twice that of the fundamental, and the second overtone will occur at a frequency that is approximately 3 times that of the fundamental. But if you do the maths, you will see that in fact the first overtone is slightly less than twice the fundamental, and the second overtone is slightly less than 3 times the fundamental. If we've got a molecule where the anharmonicity constant is very small, then our fundamental frequency, ν0, is approximately equal to ν-e. But if it is not small, or if you just want to be accurate, then our fundamental frequency, which is rigorously defined as the energy of V equals 1 minus the energy of V equals 0, is equal to ν-e minus 2 ν-e chi-e. So this is the equation that enables me to convert ν0 to ν-e or vice versa. ν0 is equal to ν-e minus 2 ν-e chi-e. Remember, this was our spectrum for carbon monoxide in a solution of carbon tetrachloride. And we have our fundamental band here, which is the V equals 0 to V equals 1 transition, and we could see it was occurring at 2170 wave numbers or so. So this observation was due to the fundamental band. It is not surprising that we can't see any additional features such as hot bands and overtones. We are not looking at a spectral range large enough to see the overtones, and the first hot band is probably swamped underneath the fundamental band. The fundamental band is a fairly broad band, and the first hot band would be centered at approximately 50 wave numbers less than the fundamental band. So given that it has a much smaller intensity, it will be completely swamped, and so the only feature you can see is the fundamental band. In part 1, I showed you these two figures for carbon monoxide in gas phase. The one on the left is for a measurement at low resolution, and we get this kind of feature appearing, where you've got two peaks separated by some gap that I said is roughly 55 wave numbers. At high resolution we got these two bands of lines appearing, and the lines are almost equally spaced. So we need to explain these two bands, and the reason why we've got this additional structure. Notice that the spacing between the lines in the high resolution measurement is of the same order as for the carbon monoxide rotational structure. and you'd be right in guessing that this structure is due to the rotational structure of the molecule. We have the selection rule for the harmonic oscillator, which is delta V is equal to plus or minus 1. But the molecules are not just vibrating, of course, they are rotating as well. They do have rotational energy in addition to the vibrational energy. And at the same time as you excite a vibration, you will necessarily have to change the rotational energy of the molecule, because the rotational selection rule, delta J is equal to plus or minus 1, still needs to be adhered to. It doesn't matter if we are looking at a vibrational transition or indeed an electronic transition. The rotational energy of the molecule will also have to change, or at least we have to conserve the angular momentum that we have in a transition. We cannot conserve the angular momentum with a pure vibrational transition in a diatomic molecule. That is one that doesn't change its rotational state, and that is because the vibration in a diatomic doesn't involve any angular momentum. So the angular momentum of the photon cannot go into the vibration. It can only go into the rotation, because that is the only thing in a diatomic molecule that has angular momentum. This is the end of part 5 of this week's online lecture. Please continue on to part 6.